Now we are going to discuss the differential equations. You all are familiar with the algebraic equations like x cube plus y plus x equal to 0, or y plus log of mod x plus x square equal to 0. These are called algebraic equations because they involve only the variables x, y, or any other variables. But if the equation involves the derivative of one variable with respect to x, like dy by dx, or the second derivative of y with respect to x, third derivative, etc., then these equations are called differential equations. A differential equation can be written in this form: dy by dx plus y equal to 0. So this is a differential equation. Or I can write d2y over dx square plus dy by dx plus y equal to 0. This is also a differential equation. So this is how we define the differential equation. These are called the equations in which we have only one variable, that is y, which is differentiated with respect to x. So this is called a simple differential equation. And we may also have the differential equations in which the function is like z is a function of x and y. So these are called the ordinary differential equations, and z is a function of x and y. And if I write the equation del square z by del x square del square z by del y square equal to 0, this is a partial differential equation. Because z is differentiated with respect to x and with respect to y also, it is a function of two variables, so it is called a partial differential equation because it is partially differentiated with respect to x and with respect to y. So there are other differential equations also. So first we will be discussing these differential equations, and remember that the differential equation must be a polynomial in y dash, y double dash, y triple dash, etc. Y dash is dy by dx, y double dash is second derivative, y triple dash is third derivative, and so on. So this is how we define the differential equations. Now there are two other terms like order of a differential equation, order and degree. First let me discuss the order of a differential equation. So what is the order? Order means the highest derivative involved. In the differential equation is called the order of the differential equation. Here you can see this involves only the first derivative, so first order differential equation. This involves highest derivative is second, so second order differential equation. This is how you can define the order. Like if I write d3y by dx cube plus d2y over dx square into a plus b dy by dx plus y equal to 0. So this is third order differential equation. Now comes the degree of a differential equation. Degree is something which must be defined first of all. So this condition is required to be fulfilled. What condition? That the differential equation must be a polynomial in terms of the derivatives, first, second, third, fourth, whatever is present. If this is not a polynomial, degree is not defined. So if I write an example, sine of dy by dx plus d2y by dx square equal to 0, then here the order of the equation is 2, because we have only second derivative involved along with first, so highest derivative is second. So order of the equation is 2, but because it does not form a polynomial, so its degree is not defined. Now you can have an equation d2y by dx square whole square plus dy by dx plus y equal to 0. Now can you identify the order and degree? Here we have two variables, two differential coefficients, second and first. First is having a power 1, second is having a power 2. What is the order? Order of this equation is clear that this is equal to 2. What is the degree? Degree is the power, maximum power of the highest differential coefficient. What is the highest differential coefficient? Second, and its maximum power is 2, so its degree is also 2. So it is second order, second degree. So you can see that degree must be defined first, and order is the highest differential coefficient this is having. So this is how you can define the order and degree, and let me discuss few more examples of this order and degree. We have y equal to 1 plus dy by dx plus dy by dx whole square 1 by 2 factorial . So this can be written as, this is 1 plus x square by factorial 2 and so on, e to the power dy by dx. So taking log of both sides is dy by dx. So this is a differential equation, and you can see that its order is 1 and its degree is also 1. Then let me take another example. d2y by dx square whole raised to the power 2 by 3 is dy by dx plus 2. Here the power is a fraction. So what we have to do is we have to convert this power of the highest derivative into an integer. So taking cube of both sides, raised to the power 3. Highest derivative is 2. So order is 2. As far as degree is concerned, this is a polynomial, degree is defined. So degree, as I told you, is the highest power, maximum power of the highest derivative. Highest derivative this has a power 2, degree is also 2. This is how you can define. Then I can take another example. d2y by dx square is equal to x log dy by dx. So as far as the order is concerned, it is 2. Highest derivative is 2. As far as degree is concerned, what do you think? Degree is not defined because this is not a polynomial in dy by dx. So this is how we define the order and degree of a differential equation. Now there are several types of differential equations which we will be discussing, and the methods to solve them. But before this, let us discuss how a differential equation is formed and how we can solve a differential equation. Suppose the question is that y is equal to a cos x plus b sin x, and you have to form a differential equation of this where a and b are real numbers. If I find the first derivative, minus a sin x plus b cos x. If you find the second derivative, minus a cos x minus b sin x, which is equal to minus y, or d2y by dx square plus y equal to 0. This is the required equation with order 2 and degree equal to 1. So this way you can form the differential equation. Another example can be y equal to e to the power minus 3x, and we have to find, or we have to prove, that the differential equation is y double dash plus 6y dash minus y dash minus 6y equal to 0 is the differential equation found by this. So if I differentiate this, y dash dy by dx is minus 3 to the power minus 3x, then the second derivative is minus 3 e to the power minus 3x, 9 e to the power minus 3x. So you can put the values in the equation. So this gives 9 e to the power minus 3x minus 3 e to the power minus 3x minus 6 to the power minus equal to 0, or this is the required differential equation which we had to prove. So in general we can say that differential equations, what they represent a family of the curves What is a family of the curve? We have discussed in integration also and in differentials also the family of a curve. What is represented by this equation? What is r here? R is the radius. This is the equation of a circle with center equal to 0, 0 and radius equal to r. This radius is r. So if you put the value of r for different values of r like 1, 2, 3, 4, you will be getting different circles which are having same center, means concentric, and are having different radii. So how can we represent this? If I differentiate both sides with respect to x, so 2x plus y square is 2y, dy by dx, r is a constant, at any time it is equal to 0. So dy by dx plus x into y is equal to 0. So this is a differential equation which represents a family of concentric circles having different radii. Similarly, see, y is equal to mx plus c. What is this? This is the equation of a line which is having slope equal to m. Slope is the angle made by this line with the positive direction of x-axis, and c is the intercept it is having on the y-axis, positive or negative side depending upon its value. So if I differentiate this, dy by dx is equal to m. C is a constant, its derivative is 0, x is having derivative as equal to 1, m is a constant, m into 1. So this represents that m is the slope of this equation. Suppose this is one such line. It is making an angle theta, and tan theta is equal to m with the positive direction of x-axis. So if you take different values of m, like m equal to 1, m equal to root 3, angle is 45, 30, 60, 1 by root 3, 30, m is equal to minus 1, 145, and so on. And different values of c, like I write the equation y is equal to x. Here c is 0, m is 1. Y equal to x root 3, m is root 3, c is 0. And you can plot these lines and you will find that this equation represents a family of straight lines having the value of slope and intercept given in this form. So this is how we can represent a family of curves given by a straight line. So dy by dx here is equal to m. This is the equation of a family of straight lines. We can put the value in this equation. Y is equal to, in place of m, I can write dy by dx, x dy by dx plus c. So this is the equation of a family of straight lines having intercept c. If c is 0, then y is x dy by dx. So this represents a family of straight lines passing through origin. So this is the geometrical meaning of the differential equation. Now we can solve some examples from this part. One such example is y is equal to a sin x plus b. This is the equation. We have to form the differential equation representing the family of curves shown by this, where a and b are arbitrary constants. So differentiate this with respect to x. Differentiating again, or this is minus y. This is the differential equation. Now if I have the equation, what does this represent? This is the differential equation which represents, sorry, this is not different, this is the equation, and the question is, form the differential equation representing the family of ellipses having foci on x-axis and center at the origin. So this is the equation of the ellipse. For different values of a and b, they represent the family of the ellipses having center at 0, 0 or the origin. Now we have to find the differential equation from this. So if I differentiate this equation, 2x by a square with respect to x, zero, or dy by dx is equal to minus a square by b square y by x. Now we can further solve this equation by again differentiating So this gives y x upon y dy by dx minus a square over b square. So you can differentiate this again by using the formula of the derivative of u by v, where u and v are both functions of x and y. Now let us solve this. So I can write dy by dx is minus x, this is x upon y, or y upon x. Differentiating both sides with respect to x. So y upon x. Now first I am using the principle of u into v, u into dv by dx, d by dx of dy by dx plus v into d by dx of y upon x, d by dx of y upon x. Here we are using the principle of u upon v. So x into differential of y dy by dx minus y into differential of x is 1 by x square into dy by dx. This dy by dx is equal to 0. Differential of this is, because this is a constant, or y by x d2y by dx square plus dy by dx, this has been written here, multiplying this inside the bracket, x into dy by dx upon x square. So 1 by x dy by dx whole square minus y by x square dy by dx equal to 0. Multiplying by x or taking the LCM, this equation becomes xy d2y by dx square plus x dy by dx whole square minus y equal to 0. This represents the family of such ellipses, eccentric ellipses. This is how you can solve such an equation. Then next question is, we have to form the differential equation of family of circles touching the x-axis at origin. If I draw the figure for this, then this is a circle touching the x-axis at origin. Another circle. These are not concentric circles. Similarly, you can show another circle. So we have to find the differential equation for this. This is the center of the first circle. Now suppose the radius of this circle is b. So center is, this radius is b. So coordinate of center is first circle 0 b. B is the radius. So the equation is x square plus y minus b whole square equal to b square. The radius of such a circle is b. So this represents the family of the circles where b is a constant. Now this equation can be written as differentiating both sides, equal to 0. So this becomes the differential equation. We can further solve this. Two can be taken common, so x plus y dy by dx is equal to b dy by dx. Now we can solve this equation by substituting the value of b from the this equation in the initial equation. So value of b from here can be substituted in this equation. B is x plus y dy by dx upon dy by dx whole square. Sorry, not whole square. B square will be cancelled. In this equation you have to put the value. So x square plus y square equal to 2by, 2y into this is the equation, and you can write the value of dy by dx from this by solving just like a linear equation. Dy by dx you can find, which is equal to that means we have eliminated the constant b from this equation, so this represents the equation of such circles. Now next to this we have to find the differential equation representing family of parabolas touching the vertex at origin, having the vertex at origin and x-axis is the positive x-axis as their axis. So we can show the figure first. This is one such parabola, another parabola having same axis, another parabola. So this is the family of such parabolas. We have to find the differential equation. You know that y square equal to 4ax is the equation of such a parabola. Differentiate both sides with respect to x, 4a, or y dy by dx is equal to 2a. Now put the value of 4a or a in this equation. (4a into x). So this becomes the differential equation. Y square minus 2xy dy by dx equal to 0. This represents such parabolas or a family of the parabolas. Now this is, till now we have discussed what is a differential equation and what is the geometrical meaning of the differential equations. Now after this we can solve different types of differential equations in the next discussion.